if we've got negative 2x plus 3y is less than or equal to 6, what this little GeoGebra worksheet does is it evaluates the expression on the left-hand side at the particular point in the plane. Say the point is 8, 4. So it takes 8 and substitutes it for x. It takes 4 and substitutes it for y. And we have negative 2 times 8 plus 3 times 4. I think that's exactly negative 4. Negative 16 plus 12 does in fact equal negative 4. Is that less than or equal to 6?
Equal. No.
Well, negative 4, yeah, negative 4 less than or equal to 6, definitely true. So, so it puts a blue dot there. Now, if I move that blue dot somewhere else, maybe right there. Let me go ahead and snap to a pair of integers there. 7, 6. Now, GeoGebra evaluates the left-hand side, and it gets positive 4. Is positive 4 less than or equal to 6? It is. So that would be part of the solution set. But just barely, though, if I move much farther there. Oh, the point 7, 7. Negative 2 times 7 is negative 14. 3 times 7 is 21. And negative 14 plus 21 is 7. It tells us that there. 7 is not less than or equal to 6. That's a false statement. And the dot is red, signifying that it's not a solution to that inequality. Now, if we want to get an idea of what the solution set looks like, it's all the blue points. So if we move this thing around, wherever there's a blue point, that's part of the solution region, we'll call it. But if it's a red point, that's not part of the solution region. So one way to do this is maybe plot several hundred points and just look to see, okay, where are the blue points, where are the red points? In practice, not a good idea, but with GeoGebra, it works out pretty well because it'll trace them. So just kind of move this around. Any point that's blue is a solution to the linear equation. So it's looking like this. But if we stray over here, the red points are not solutions to the linear inequality. That's what I meant to say, linear inequality. So we just kind of do more of this. Blue points, these are solutions. Red points, these are not solutions. And we kind of get an idea where the boundary is. There's a boundary somewhere where on one side of that boundary we get solutions, and on the other side of the boundary we do not get solutions. And I'm thinking it's right in there somewhere. In fact, it's the graph of the equation negative 2x plus 3y equals 6. If it's exactly equal to 6, it's on this straight line. Now some of the dots have radius of positive values, so you can see some blue creeping across the line one way and red creeping across the line the other. But in general, every point on one side of the line is going to be red, and every point on the other side of the line is blue. We want to figure out which side of the line it is, and then we'll shade that side of the line. It's easy enough. We don't have to plot 1,000 points like maybe we just did here. 1 point. If we plot 1 point, where is it? Like right there. And it makes the inequality true, we know it's that side of the line. We shade that side of the line. On the other hand, we don't know in advance. Suppose we plot that point. We don't have to plot it, we just have to check it. 3, 9. Plug it in and ask ourselves, does it make it true or does it make it false? If it makes it false, we know it's not that side of the line, it's the other side of the line. So what we'll do is we'll graph the boundary line, and then we'll choose a test point and see which side of the line. One other thing to keep in mind, if it's a strict inequality, strictly less than, we're going to want a broken line here. So I should probably erase this. The examples I've given are strict inequalities. We're going to want a, well, come on, break the line, dotted, dashed, or a combination of dots and dashes is what we want there. If it has the or equal to bar, we'll make it a solid line. And Alex has a feature where we can click on, toggle back and forth, solid line, broken line, and then click on the line itself, and then it'll make it either solid or broken depending on what we want.